Okay, good morning. So we are starting our seminar at the International Center of Physics. Our speaker today is Piotr Gładysz from Nicolaus Copernicus University in Poland. And it's nice to know that the name of this university is because Copernicus was born in Torun in Poland. So Piotr Gładysz is a PhD student in University in Torun. He works basically in quantum optics and some current topics, which include nanostructures, coherent interaction between light and polar molecules, and other modern topics of quantum physics and quantum optics. And today, the topic of his talk is about his new results on Rabi frequency in polar systems. And it's also nice to know that Piotr, I think he's in the third year of PhD studies, but he has already two important papers, one in Nature Communications and one in Scientific Reports. So now I have the pleasure to announce Piotr Gładysz to give his talk.
Thank you for kind introduction. Thank you for having me there. Yeah, I hope this presentation will not be too obvious for you, as you probably are in the field as well, more or less. However, I'd like to introduce some basic things and show how from basic things even you can obtain new results, and something which looks similar may hide some non-trivial behaviors. So nonlinear behavior of Rabi frequency, I will depict all the things in three parts. So first part I will talk about the polar systems in general. It can be polar molecules, for example. Then I will show you how to obtain this Rabi frequency from equations and what's the difference between linear and nonlinear parts. And this nonlinear behavior is the third part, where I also show you the results, recent results of the work. So let's start with the polar system. This is really basic like introduction. So we start with many energy levels in, for example, atoms in any artificial systems like dipoles, like quantum dots or stuff like that. And we say that we want only two energy levels. And I work in the resonance regime, which means that the field is tuned to the atomic frequency of the system, and actually we can just set a notation here for the ground state and excited state. So G is for ground, E for excited. So basically that's it. I work with two-level system, which is enough to see quite interesting results already. And I will of course use von Neumann equation. I can as well adjust the coherences in the system with the Liouville part or Lindblad part. However, this case I use semi-classical Hamiltonian, so the field is strong, has to be strong, so I don't have to use fully quantum description in that case. And the Hamiltonian looks like this, pretty basic stuff. We see here that this is electric dipole approximation, since I want to use strong fields with transition dipole moments, but also I incorporated here not usually used parts, which are the permanent dipole moments of the system. So if we look first on the field as well, the field is just a plane wave, so I have just one frequency. This is convenient to look at the spectrum of the system later. So if I can only drive my field with one frequency, this is much easier to calculate later. And that's the whole matrix representation of my dipole moment. So you see, these two additional parts are responsible for, are actually the most important parts for my talk or for my work in general, because these two parts incorporate differences in the evolution of the atomic system, or two-level system, let's say rather. And Let's look at the difference, actually, what these two parts, these diagonal terms, incorporate into the system. If we don't have permanent dipole moments in our system, then we just have this static case where the the excited and ground states stay in the same level. Many mosquitoes in there. But if we have these additional terms, we see that these levels here, they are not oscillates, but because it's PDF, however, it should oscillate with the frequency of the field and with the amplitude of this permanent dipoles. So you can imagine that both of levels oscillates with different amplitude, but in phase. And this is very different if we look closer into the equations compared with the static regime. And we also see here that I called it broken inversion symmetry, because usually when you get an atom, then you have transitions and you don't have permanent dipole moments, so everything looks like this. But if you broke the symmetry, actually you can have permanent dipole moments in the ground or excited or both states. So for me, more important is to use, for example, molecules, because of course in atoms it's hard to get permanent dipole moments since they are spherical. If we do not deform it with field, but even if we deform it, these deformations are too small for the results to obtain nice results. So I'd rather use molecules. So this is the example to the left of the molecule which don't have permanent dipole moments, and on the right side the one with permanent dipole moments, just to be clear. So this is the description of the system. Now we can go to the parts of Rabi frequencies. So from the von Neumann equation, we can, of course, show set of equations for the evolution of the population and the coherences in the system. And it would look like this. Rotating wave approximation is applied in here. And you see that this is basically easiest and pretty well-known set of Bloch equations. There's nothing different from the case with or without permanent dipole moments in this actually description. However, I briefly show you the parts for some of you who don't maybe know it. Here I just put gamma as a decoherences, so the inverse of the lifetime of the excited state. And detuning is here, so we are closely tuned to the resonance, so this delta is usually pretty small. But we have these two parts as well, which are the most important for this work. And first part is Rabi frequency, and the second part is the decoherences, and actually I did the ansatz I show you in the next slide. But yeah, let's focus more on these two guys. So again, we have this set of Bloch equations, and let's start with the coherences. And usually when you work with systems without permanent dipole moments, you would do this kind of ansatz, so you can remove fast oscillations of the coherences which comes from the field, from the driving of the field. And now I have to incorporate another part. So this is the first place when differences can occur. So the second part I have to use is this strangely looking thing with the kappa, which describes me that I actually have permanent dipole moments in my system. And actually the most important thing is that I need difference between these permanent dipole moments. So if I have even permanent dipole moments in the ground and an excited state, but they are the same, we would still see nothing. But here, if we got this difference, we can call a kappa, which also depends on the strength of the field and of its frequency. And we can put this ansatz into the Bloch equations, and we still get the same equations as for the case of known, as with the case where we don't have permanent dipole moments. This is pretty nice that we can do this like in that way. And we can also see that this exponential can be expressed as a infinite series of Bessel functions, and just this regular exponents with n times the frequency of the field. So we see here pretty clearly that from this part, we as well can use rotating wave approximation since we did it previously. And if we do that, we end up just with this, this guy here. This is pretty straightforward to do. If you incorporate only the terms that are solely oscillating in this sum, of course, including also this part here. And this allows us to write our system like that. But this part will be important in the next slide, since now we can focus on the Rabi frequency. And Rabi frequency, again, in the usual case without permanent dipole moments would look like this. However, if we incorporate permanent dipole moments, we have to add also this part we just showed in the previous slide. And again, kappa is the same. So you see there's the easy transition from non-permanent dipole moment to permanent dipole moment case. And also we see that if we go with kappa to 0, which seems that, for example, we go with this this bracket to 0, we see that everything's work perfectly like in the case without permanent dipole moment, since this guy behaves like that if we go with x to 0. Okay, so far so good. We got pretty much the same Bloch equations as without permanent dipole moments. However, we have hidden information about these PDMs in Rabi frequency. And now for the nonlinear behavior. Just to recall the how the Bessel function looks like. This is the first Bessel function. Second, sorry, this is the 0th. This is the first one, the second one, and so on. And as you remember, we are going to use the first Bessel function. So yes. So we would like to see how it looks for the Rabi frequency if we look at the Rabi frequency depending on the electric field, on the amplitude of the electric field. So we see here, this may be a bit tricky for the first time, but kappa, of course, contains this E, so this E will cancel out with this E, and the only dependence on the electric field would be in this Bessel function. So that's why I wrote this first Bessel function. And we see that we somehow in this simple calculation predict that, of course, if kappa is small or if the field is weak, we have linear dependence between Rabi frequency and the field. However, if we go further, we see that we should see something I called robust region, where the more you increase the field, the atoms should, or the, for example, ensemble of atoms should not feel the difference actually and should oscillate still with the same or close frequency. So this is the robust region, because if you can have an ensemble of atoms, they should oscillate in the same way, even though the field would change slightly to the left or to the right. However, and there is also predicted, let's say, a more interesting part with the collapse region, where we see that if we even further increase the electric field, we see that the oscillations should goes down, which is pretty strange. And that's actually the case why we wanted to investigate more this phenomenon. So the basic question, the fundamental question for now is it true, or is it just because of the approximations we did? So let's start with some very basic calculations here. So we see this is the Rabi oscillations of the two-level system, perfectly tuned, so into resonance. And for different cases, when we don't have permanent dipole moment difference and when we increase it. And you see there that for the blue and orange lines, they are basically the same. You can see here that they start to differ a bit. However, if we increase it more, we see, as predicted, that the Rabi oscillations are getting to be smaller than for the same amplitude of the electric field. So this is preliminary result, the simplest possible. However, before I go further for the more interesting part, I can assure you that there are systems we can use to obtain such behavior in real life. And I like this molecule, lithium hydride, which is nice because we can use their rotational levels. And if we go for the ground electronic state sigma plus of that, and use its rotational states, J is the total angular momentum and M is the projection onto the z-axis or in the lab frame, for example, then we can see what's the value of the dipole moment in this system. And of course, we have to incorporate something called lab frame, right? So if we got gas of molecules like this, for example, they rotate and all these dipole moments are averaged to 0 if we do not order them. So we have to use a regular electric field, like a static one. And with that, if we increase this static field, this is the increase of the static electric field EDC, we see that from 0, this is the permanent dipole moment in different states. So we see that this permanent dipole moment, for example, goes up for the ground state if we increase the DC field, which means basically that we order these molecules. And we can see from this graph which transitions are the best for us to obtain the greatest difference between dipole moments, permanent dipole moments. And of course, between green and blue is the greatest difference. And this dashed line is actually to notice that this is the threshold for the laboratories. So people are not able to create fields, DC fields stronger than to the right of this dashed, but that's enough for us. This region is also very nice and gives us, for example, here pretty nice difference. So that's the one part. And we can as well calculate transition dipole moments in that case. Again, depending on the DC electric field here. And we see that, for example, for this transition we are interested in, 0, 0 to 1, 0, which is the orange one. In here, we see that the transition dipole moments is also parallel to the permanent dipole moment. It's okay, but we can as well find from this picture, for example, other transitions where the permanent dipole moment is perpendicular to the transition dipole moment, which for some cases can be more important. However, for this case, it doesn't matter for us because we have to incorporate at least DC field and the driving field anyway. So that's it. So that's it for the real life example. And now we can go back to some concerns which I maybe showed previously, which means that if we use this expansion, we use only 1 or 2 elements of this expansion, and the question is that enough for us or not? So now let's look at the recent results. And the first thing first is how we can actually measure the Rabi frequency of the system. So I think that the best way is to calculate the dynamics of the system. So this is the population in time. And also you can see here that I incorporated some decoherences in the system. And we can calculate from that spectrum of the system. And if you are familiar with that stuff, you know that spectrum looks like that. So there is a central peak at the frequency of the field, driving field. And there are side bands or side peaks, which are precisely on the plus minus Rabi frequency of our system. So that's a good idea to look at this part here, right? So I can calculate the evolution of my my atomic system. I can calculate the spectrum, and then I can look on this smaller peak here, and I know that the position of the peak is on the Rabi frequency. So why don't you use it? And that's how it looks for the weak field. So for the weak field, you see there are many things here, but this is pretty basic. I compared the results for the with permanent dipole moments and without permanent dipole moments, basically, and you see that they are pretty close together. So in the weak field, there is nothing interesting in here. However, if we can go further, we can go to the strong field regime. And in strong field, it's getting much more interesting. Here, this is basically the close-up of this the evolution, however, taken something like here and closed up a bit. So this is the evolution in different cases. So if we can track this, the blue line is the oscillations of population if we don't have permanent dipole moments. They are pretty fast, actually. And then we can as well calculate, and this blue line is with the rotating wave approximation. However, we can as well calculate it without a rotating wave approximation, which is this orange line here. Right? So you see the oscillations of the field as well, this fast oscillating part, and they are pretty much the same. So for this case, it works pretty well. However, we can go now to the permanent dipole moment case, and the red one is the most important for us because or maybe let's start with the green one. Green one is the case where we have permanent dipole moments, but we use rotating wave approximation. So this is this green line. We see that the Rabi oscillations are indeed smaller than compared to the case without permanent dipole moments. But if we also incorporate all the terms, so we do not use rotating wave approximation, we have this red line right here. So this is the one here. Also, it behaves comparable to the green one. However, you have these fast oscillations. And there are also several orders I tried. So I just take more elements from this expansion and look if they follow or not the exact solution, the red solution. And it looks like to the fourth order, it's already pretty okay. However, do we really need to go to the fourth order? So the question is, if we use rotating wave approximation, is it enough for us to predict what is going on or not? So this is the actually left side of our model triplet. So we see here that if we don't have permanent dipole moments in the system, then the rotating wave approximation is the blue one. Without rotating wave approximation, it's an orange one. They are pretty okay, pretty at the same point, -4. While here we see that the red one is here, so the perfect one is here, while the rotating wave approximation one is here, this green. So they are a bit apart from each other. However, it's not that bad. And if we incorporate more terms from this, we can go from the rotating wave approximation up to there pretty quickly with the fourth order almost on the red one. So that's it. However, we can also see how it will look for different values of the strong field, or in general, electric field. This is the most, for me, fun plot and most interesting. If we don't have permanent dipole moments, and now we look on the right part of the Mollow triplet, so this right side band, and I did calculations for many values of electric field. This is the arbitrary units, and I goes from 0 to basically 8, step 0.2, and we see that if we don't have permanent dipole moments, the peaks are, as expected, linearly dependent on the electric field itself. Sorry, this should be this. Yeah, this is frequency because this is the spectrum. So the Rabi frequency depends linearly on the electric field. However, if we incorporate permanent dipole moments, we see that it starts the same. However, then if we increase the field, it goes there, and it starts to bend and goes back in. So we see that, and these calculations were obtained for the full Hamiltonian, so there is no rotating wave approximation in these calculations included. And to clarify the picture, we can plot it like that. So we put field's amplitude, and we can see the Rabi frequency value. And if there is no PDMs, we know that it's supposed to be linear. However, for the stronger fields, we see that in that case, it's supposed to be linear in the rotating wave approximation, while with PDMs, it's supposed to follow the first Bessel function. So this is the Herbois rotating wave approximation. However, the points are points taken from these pictures. So we see that for stronger fields with no PDMs, we should also incorporate non-resonant terms to say that to describe what is happening with these points, because they are not going to along this line anymore. However, here we see that even though we use here for this solid line only first term, so the rotating wave approximation, we see that the points are pretty much following this curve, even if these points are calculated for the whole Hamiltonian without approximations. So this is basically it. And for some kind of take-home message, we can I can recall that the idea for this project was to look if really this behavior can be observed in any systems. The concerns were, of course, like that. So if we can use rotating wave approximation or not in that case. And it turns out that actually we can use rotating wave approximation, and the results are at least qualitatively the same, which is nice, of course. And the interesting thing here is that if we can find molecule which has much greater permanent dipole moments than the one used here, we can even use very weak fields and also see something like that. So the next step, let's say, for this project is to calculate it for realistic molecules which has much greater permanent dipole moments, or maybe something artificial like quantum dots, where you can have much larger permanent dipole moments between systems. And that's it for now. Thank you.